It's now time for CAPE Physics. I am your teacher, Paul Bender. Today, I will be guiding you through charged particles in an electric field. Now, this topic is part 2, because the last time we met, I had done part 1 of charged particles in an electric field. And so this lesson today is a continuation of that. And so just to remind you on what it is that we had done the last time. The last time we had looked at electric field. We had determined what is an electric field and the characteristics of an electric field. And we went more into uniform electric fields and how uniform electric fields affected charges. And we looked on how to calculate the force on a charge in an electric field. And then we also looked at how the electric field is used to accelerate electrons and charged particles. So today we will do 2 things, and these are the objectives of today's lessons. All right? So at the end of this presentation, you should be able to make calculation relating to a charged particle moving vertical to a uniform electric field, to determine the magnitude and direction of the force on a point charge due to the presence of another point charge, and determine the magnitude and direction of the resultant force on a charge due to the presence of more than one other charges. Okay, so we'll just extend what it is that we had done, because we are looking at charges in an electric field. And when 2 charges are close to each other, they are in each other's electric fields. For instance, the moon is in the Earth's gravitational field and the Earth is in the moon's gravitational field. They're mutually in each other's field. And so let us see what we have here. So we will start with the motion of a charged particle perpendicular to a uniform electric field. Remember, a uniform electric field, the field lines are straight, and so if the field lines are vertical, then the motion of the particle will be horizontal. So let's consider this situation. 3 particles traveling at the same speed enter into a region with downward electric field. They travel along the paths illustrated, and this is a little thing. So these 3 particles are moving. They are moving across. So 1, 2, 3 particles. One went that way and one went that way. So those 3 paths the particles went along. So we're going to consider that situation, and we're going to ask a couple of questions. All right? So, which particle is likely a proton? Which particle is likely a proton? Now remember, when a particle is positive, the force that it experiences is in the direction of the electric field. When a particle is negative, the force that it experiences is opposite to the direction of the electric field. That is what we would have discovered in the last lesson. And so from here, we can see that since the red charged particle moves upwards in the direction of the electric field, it suggests that it is experiencing a force upward. And so the red particle is likely a proton. Then ask, which particle is likely a neutron? Now, a neutron has no charge. And so this neutron, remember we talked about compatibility with the field, right? When the neutron is incompatible with the field because it's not going to experience any force. And so if it is passing through the field, then it will be unaffected by whatever happens, by the field. And so more than likely, the likely neutron is the orange particle because it is unaffected by the field. And so the neutron is and obviously the next question is, which particle is likely an electron? Well, the electron is negative and it curves downwards, which suggests that it is experiencing a downward force, and that downward force is opposite to the direction of the electric field, and so it curves downwards, and so the blue particle is likely an electron. And then the size difference also clues you in, because an electron is much, much smaller than a proton and a neutron. Proton and neutrons are about 1,800 times more massive than an electron. So that's also a little clue. So the blue particle is likely an electron. So what are the explanations? What it is that is really happening, right? And I gave an explanation, right, where it says that the positively charged proton has an upward force on it while it travels through the field, so it goes upwards. The negatively charged electron has a downward force on it while it travels through the field, so that goes downwards. And the uncharged neutron has no force perpendicular to its path while it travels through the field, so that goes straight across without being affected by the field. Okay, and so this technique is used in charge separation, in velocity selection, a number of techniques it is used in order to knowing that these charged particles will separate because of the electric field. Okay, and so if you have a bunch of particles and you want to separate them, and you only want positive charges or negative charges, you can separate them by passing them through an electric field. Okay, so here's a little sample question I want us to do in where this technique is used. It says a negatively charged particle of mass 1 microgram and charge 2 microcoulombs is traveling horizontally with a velocity of 8.0 by 10 to the 3 meters per second and enters a region with an electric field of magnitude 3.2 by 10 to the 5 Newton per coulomb, vertically upwards. So that's the magnitude and direction of the electric field. Calculate how far below its point of entry the particle would be after it has traveled the horizontal distance of 0.8 meters in the field. And for this, we're going to neglect friction and gravity. All right, friction because more than likely this thing is happening in an evacuated space, and we're going to neglect gravity because the mass of the particle is small in relation to the force that would be exerted on it. Okay, so that's why we can neglect those two. So let's look at the solution. All right, so the solution, here we have the particle, and the particle, we want to look at what it is that the question is really asking us. The question is asking to find the distance d after the time for which the electron is in the electric field. So here the electron is traveling, let me go back a little bit. Here the electron is outside the field. This is the region of the field here. So the electron is outside the field. So the electron comes, it enters the field, and because of the force that is exerted on it, it takes that path. So what the question is asking, how far? This is the horizontal. If it were going straight, it would be this. How far down does this charged particle go as a result of going into the field? All right, so let's look at the solution now. So in the solution, what we need, if we need to determine how far down it goes, first of all, we need to determine the time for which it travels in the field, and then we're going to determine the force due to the field on the electron and the downward acceleration of the electron. Now, the electron travels a distance of 0.8 meters in the field, and after it travels the point in a particular time, well, at a particular velocity. And so we know that time is equal to velocity over distance over velocity. All right, and so we can calculate the time for which the electron is in the field. And so the time is the distance traveled is 0.8 meters, and the velocity is 8.0 by 10 to the 3 meters per second. And so the time is 10 to the negative 4 seconds, all right? 10 to the negative 4 seconds. That's the time for which the particle will be traveling. Now remember the force due to the field on the electron. Once the electron enters the field, it will experience a force given by the electric field times the charge on the electron. All right, remember force is equal to electric field strength times charge. And so when we look at that, we will see that the electric field strength is 3.2 by 10 to the negative 5, 10 to the 5 Newton per Coulomb, and the charge on the electron is 10 to the negative 6 coulombs. And when you multiply that, you get 0.64 newtons. All right. And then the downward acceleration. So because this charge is traveling in an arc, it has an acceleration downwards, a vertical acceleration. And so we're going to calculate that. And we know from the laws of motion, the acceleration would be the force exerted on the particle divided by its mass. Force divided by mass is acceleration. And so when we look at the force, we work that out to be 0.64 newtons. The mass of the particle is 10 micrograms, and that would be 10 to the negative 6 kilograms. All right, good. Okay, and so 10, all right, was it 10 milligrams? That's something wrong here. All right, so using the equations S equal ut plus half at squared and considering the vertical motion of the particle, we can work out d because vertically the particle is moving like this. So when it enters into the field, it has no vertical component of acceleration. It just has a horizontal component of its acceleration. And so when it enters into the field, it has no vertical component. And so the horizontal component, the vertical component initially of its velocity would be 0. And we use Vd is equal to ut equals half a. We worked out the acceleration. And this is the time for which it travels, t squared. And we will get that the distance it travels is 3.2 by 10 to the negative 3 meters, or 3.2 millimeters. If you cast your mind back to when you did projectile motion in mechanics, you will see that this is very similar. As a matter of fact, it is the same kind of motion that this particle would be describing in this electric field, because when a particle is projected horizontally, if it's projected off of this disk and it's projected horizontally, it will travel like that. And the reason it travels in an arc because it has a downward gravitational force. When the particle entered into the electric field, it experienced a downward force which pulled it in an arc. All right, so it's the same technique that we use to that mechanical principle in this topic area. All right, and so that was just to kind of wrap up what we did with uniform electric fields and how that was used. All right, so we'll move on to another aspect of charges. Remember, we're looking at charges in electric fields. That's what we're looking at. We're focusing on that. Charges in electric fields. Once a charge is in an electric field, it will experience a force. It will experience a force once it is in an electric field. And so, if we have charged objects in some close proximity, right? Charged objects in proximity. So when two or more charged objects are brought in close proximity, they reside in each other's electric field. This charge has an electric field, and this one has an electric field. So this charge is in the electric field of this one, and this charge is in the electric field of they are in each other's electric field. And so as a result of being in an electric field, they will have forces exerted on them, all right? As a result of residing in the other's field, forces exerted on all the charged objects. So I am in your field, so you exert a force on me. You are in my field, so I exert a force on you. And it is so when we gather. Each of us, we have a gravitational field associated with us. So we all attract each other. I'm attracted to you, you're attracted to me, and so on. But the attraction is so small that we don't even notice it, okay? But we all exist in one another's, and we all exist in the Earth's gravitational field, which is so much larger than we can produce to each other. All right. So the electric field of a point charge. All right. So the electric field due to a point charge is a radial field. It means it starts at the center, and a point charge is just a charge that, for all intents and purposes, has no dimension. If you have a spherical object and you charge it, just as we said that the center of mass is an imagined position at which all the mass of an object appears to be concentrated, in the same way, when we have a spherical object, all the charge is imagined to be concentrated at the center of that sphere. And we can consider it to be a point charge, a charge without any dimensions. All right? And so the field is a radial field, and this is the field due to a negative charge. And remember, this is consistent with what we said, how we would determine the direction of a field. If we take a positive test charge and we place it anywhere here, it will be attracted to the negative charge, and that is the direction in which the field would go. And this field is a radial field. It goes radially outwards. What we also see is that this field is also, the strength of the field decreases as you move away from the field, all right? So here, the field lines are closer than here. And so the field is stronger here than here. Remember, when we looked at a uniform field, all the field lines were parallel. They were the same space apart, which suggested that the field is a uniform field. Here, this suggests that this has greater space than here, that the strength of the field is less than here. Okay? So it's a radial field. And also we also call it what is called an inverse square law field. All right? We will get that. And the strength of the field decreases with distance from the charge. All right, electric field of a point charge. Still, the electric field strength at a point P at a distance r from a point charge of magnitude q. So we have a point charge q, positive q. We have some point P at some distance r from the center of that charge, and it is given by this relationship here. E is equal 1 over 4 pi epsilon 0 q over r squared. Q, of course, is the charge, r is the distance, and this 1 over 4 pi epsilon 0, the field is said to have spherical symmetry, and hence the 1 over 4 pi attends to that spherical symmetry. And epsilon 0 is a property of the material or the matter in the air. It's called the permeability or the permittivity, of free space, or the permittivity of air. How much the air allows. It's a factor that tells how much the air allows this electric field to spread out within it. All right? So the 1 over 4 pi is to account for the spherical symmetry. The field forms a sphere around the charge, as we would have seen. And Q over R squared, of course, are the charge and the distance, right? So that's for the magnitude of the electric field. And we can determine the direction of the electric field by just putting a positive test charge in the field, and we see that will move in that direction which is, say, that will give you the direction of the electric field. So this E equal 1 over 4 pi epsilon 0 Q over R squared is the magnitude of the electric field. All right, so the electric field strength at a point at the direction of the electric field strength at P is radially inward or outward. So if this were a negative charge, it would be radially inward. Since this is a positive charge, it's radially outward. Okay. So the force on a charge in the field of a point charge. So if we put a charge in the field of a point charge, it will experience a force, right? So if a charge of magnitude Q is placed at P, it will experience a force of magnitude. So you remember, force is equal to electric field strength times charge. And we have our electric field strength is equal 1 over 4 pi epsilon 0 Q over R squared. So if we want to multiply that by the charge Q, then we will get the magnitude of this force here. And so that would be 1 over 4 pi epsilon 0 Q dot little q, which Q times little q, over R squared. And so that would be the force exerted by the charge positive Q on the charge little q, by capital Q and little q. But remember, Newton's third law tells us that if an object A exerts a force on an object B, B will exert an equal but opposite force on A. So capital Q exerts a force on little q, and little q will exert an equal and opposite force on capital Q. All right, so the forces are what you call Newton's third law forces. They are equal and opposite. You know, we exert the same force on the earth that the earth exerts on us. But it's just that the earth is so big we can't move the earth towards us. But the earth can move us towards it. All right, so Newton's third law forces are applied here. Okay, and so this is an equation to remember, and this equation is termed Coulomb's law. And for 2-point charges that are a distance r apart. Okay, that's Coulomb's law. Didn't specifically say so, but that's what the law is. Okay, so how is the direction of the force determined? All right, I will leave that with you, because we have looked at how the direction of the force is determined. All right, the arrow shows the force going one. And remember, unlike charges attract. And that's about it. Okay? All right. Force on a charge in electric fields of more than one charge. So we're going to look, this is two charges, two mutual charges, right? So if we have this situation, consider 2-point charges at some distance apart on a line joining their centers. So that's one is the same big Q and little q, right? One positive and one negative. A third charge is placed at some point between the charges. So we play a third charge, negative capital Q, all right, between those two charges. What happens is that the third charge is in the fields of the other two charges and will experience forces due to both fields, all right? So this third charge here, let me go back. This charge is in the field of this charge, and it is also in the field of this charge here, because all of these charges have fields going out, and this one has fields going out. So this charge is in the field of both of these. So it will experience a force due to this charge, and it will experience a force due to this charge. All right, this force will be a repulsive force because they are the same charge, and this force here will be an attractive force because they are opposite charges. Okay, so we go forward with that. So here we see the forces being exerted, right? And this is the force due to capital Q. This is the force due to common Q. Okay, and so the net force on the third charge is the vector sum of the other two charges. So you have to add these as vectors. As it is, this is simple. Because both forces are along the same line, they're in the same direction, so in order to get the magnitude of the resultant, you will just add the magnitudes of those two forces because they're acting along the same line. But remember, you must, to get the net force on the third charge, you must take the vector sum of the forces due to the other charges, right? If they were in opposite directions, you will have to subtract them, okay? All right, so force on a charge in electric fields of more than one charge. We're continuing with this. Suppose the distances are R1 and R2. All right, the distances are R1 and R2 are shown. Okay, then the magnitude of the net force would be the magnitude F capital Q plus the magnitude of F common Q because they are both in the same direction. So we will just add the magnitudes of the forces there. All right, so when we add the magnitudes of the forces, we will get that, and you can do this for yourself, you can do the mathematics for yourself. F capital Q, right, F capital Q 1 over 4 pi epsilon 0. Ooh, this is supposed to have a Q there. All right, I want you to make a correction. This ought to have a capital Q here and not 1 over 4 pi epsilon 0 because you remember we're looking at forces, and so this ought to have a capital Q here. So please, when you're going to look at this equation here, you must replace the 1 by a capital Q, okay? And then you can expand the brackets here, and you will see that you will get the force due to the discharge plus the force due to that charge in separation. Once again, just let me remind you that you're going to put a capital Q here instead of the 1. Okay, that's an error on my part in preparing this lesson. All right. Okay. So here's a little sample question. It says, at which position would the net force on a charge negative Q be likely 0? And so the charge, we had 3 positions, all right? In which position it would be likely 0? Is it 1, 2, 3, or none of them? All right, so those are your options. Let's look at position 1. Now at position 1, it was a negative charge. So if we have a negative charge here, this charge will attract it this way, so it will experience a force that way. All right, maybe I should draw it. All right, so what we have is a positive charge. We have and a negative charge, and we have 2 positions here. And so if I put a negative charge here, a negative Q, then this will experience, this charge will give it a force that way, and this negative charge will push it this way, all right? So that is what that charge, negative Q, will experience at this position. So these two could never add up to 0 because they're both in the same direction. So it can be this. If I put the negative Q here again, this will experience a force this way, and this will experience a force that way. So it is not likely that these two could ever add up to 0. But if you put the negative Q here now, this force will push the charge that way, and this force, remember these are the two charges that we're talking about. This charge will pull this charge this way. Now, since these two are opposite in direction, there's a likelihood that at some point they can add up to 0. So this is most likely to be 0. It doesn't have to be, but it is most likely. These two in between the 2 charges can never be 0 because they're always in the same direction. So here is more likely 0. Okay? All right, yeah. It agree with us, right? Well, it wants to make. So here is another look at a sample question. This is saying to determine the direction in which the charge negative q will move due to charges positive q and negative q of the same magnitude. The triangle is equilateral. So the distances here are the same. This is the same distance from this and so on, right? So negative q is the same distance from these two charges here. So we want to determine the direction in which the charge negative q will move due to charges positive q and negative q of the same magnitude. And so the triangle here is equilateral. Now remember, this charge is in the field of both of these two here, right? This charge is in the field of this one and in the field of this one. So that this charge will experience a force due to this one, and it will also at the same time experience a force due to this one. So let's look at the direction of the force that this charge will exert here. That force would be radially upwards, all right? So we will have a force that is really radially upwards, okay? And this charge, because they are opposite charges, this will exert a force downwards, really radially downwards, along the line joining the two of them. So it will exert a force that way. Now these two forces are impacting this charge Q. You remember before I told you that when you're going to add the forces, you must add them as vector sums. You must sum them as vectors. And in this particular case, you just can't add these two forces and say this plus this, because you have to take the directions into consideration. Cast your mind back to when you did mechanics and vectors about using the parallelogram of forces. You would complete a parallelogram, and when you complete the parallelogram, the line joining the resultant vector would be the diagonal. And so in order to determine the force that is acting on Q, we complete a parallelogram. So we will complete the parallelogram. All right, and then when you complete the parallelogram, this force here, F, would be the resultant force. So this force, due to these two charges here, this charge Q will experience a force in that direction. And if it were able to move, then it would move in that direction, because that's the direction in which the force, the resultant force, is acting. All right, and so here is an example, and you can determine the magnitude of this force if you know the magnitude of the charges and you know the distance. You can calculate what force is exerted. You can use Coulomb's law to determine the magnitude of the force at this particular distance here, and you'll have to know the charges and so on. And when you find the magnitudes, you'll do a little mathematics to determine what that F is. All right. So it didn't really set up a question for that, but it's just to give you an idea on how other charges impact this charge when one charge is in the field of other charges. And this has multiple applications in so many of our little devices and so on that we use, where you use charges in order to direct and deflect charges and so on, and to keep them in particular pathways that you may need. So let us do a little recap. So in the lesson that we did before today, in the charges in electric fields 1, we just looked at what is an electric field, what it is. This electric field is just a region in space in which a compatible object will experience a force. And so we looked at also how charges are impacted when they are in this electric field. And we looked specifically at the uniform electric field and the characteristics of the uniform electric field. And we said we can find the magnitude of the uniform electric field by dividing the potential difference through which the electric field is formed by the separation of, because normally electric fields are formed between two parallel plates. If you have the separation of the plates and we have the potential difference across the plates, we can determine the electric field, and that will be potential difference divided by separation. Having done that, we looked at when a charge is placed in the electric field, the force that is exerted on the charge that is placed in that uniform electric field is given by the electric field strength times the magnitude of the charge. And that will give you the force. And we said that the force on this charge, if the charge is positive, then it will experience a force in the direction of the electric field. If it's negative, it will experience a force opposite to the direction of the electric field. Then we went on to look at if we release a charge at one in the electric field, then because that charge will experience a force, it will be accelerated. And we had looked at an electron welding device where an electric field is used to accelerate electrons to very high speeds. And because of the kinetic energy that they gained, they can generate enough energy and heat in order to fuse metals together. And it is used for precise welding. So that is what we saw, one use of that. And then, so that kind of concluded. And today now, what we went and we looked at an electron traveling, or excuse me, a charged particle traveling perpendicular to the electric field. And because, for instance, when we move horizontally, the Earth's gravitational field is downwards. As we move horizontally, we experience a downward force, and so everything, if we throw something, it will move in an arc. And in the same way, this electron, this charged particle, moved in an arc because it experienced a force. And then finally, we looked at point charges in the fields of other point charges and how to determine the force that, the resultant force that was acting on it. That in essence kind of sums up what it is that you will have to do with regards to electric fields.